Alright, so the next topic that we are going to see after linear regression is logistic regression. We are going to talk about the most common example that is used, which is disease detection, right? And it's a binary problem, which means that it can be a yes or a no. There are just two outcomes, right? You have a doctor looking at a medical report, and then he tells you whether the patient has a particular disease or not, right? And most of the real world problems that we face are binary. Yes, no, disease, no, spam or not, right? An email is spam or not. Maybe something is a fraud or not. The problem is that we are not 100% sure, right? The decisions that are made here have some sense of uncertainty. Now, what do we say? We say that the real question here is not yes or no. No, it's not the actual question. The actual question is, how confident are we about that yes or no? How sure are you? Right? So, we have earlier seen linear models, or we came across linear regression. You take a simple linear model which gives you a score, right? Some particular score based on some test values, right? You give it a test value. So they can give you outputs like 3, 5, minus 17, right? They can give you such values. But what are these numbers? These are certain values, right? They are not probabilities, right? They can even be negative, go above 1, right? Can have any range. Let's just say that the range is minus infinity to infinity, right? Any values. But we were saying about surety, right? We're talking about surety, which means probability. So can the probability of something be minus 17 or 3? No. Because for probability, we need an output between 0 and 1. Right? Because 0 means impossible and 1 here means certain. Right? That is what we want to understand. Right? So there is a requirement of having probability. Right? You want to know the probability of a disease. Kitna likely hai, right? And you don't want a raw score, right? But what exactly does the model do? The model makes or finds a score, right? It generates a score. But because of the maths that we know, we put this score through a function. And what does that function do for us? It compresses everything into 0 to 1. So the range is 0 to 1, which is done by that function, right? So this is the point where a special curves comes in, right? You have a special curve, and by that curve I mean the sigmoid function, right? For example, you have x-axis, which is the model score, and you have y-axis, which is the probability, right? And you have an S-shaped curve, right? Let's just say it's something like this, right? Maybe even a little closer to 0 or a little higher, but actually of this particular shape, right? So a very negative score, right, would mean that the probability is close to 0. Let me just redraw it and show it like how it really is. You have 0, right, and you have positive values on the right hand side, the negative ones on the left, and this is your probability. So the function actually looks like, right, so this is your 0 for your y-axis, right, and this is your 0 in the middle. On the right you have positive values 1, 2, 3, and on the left hand side you have -1, -2, right? It can go to a particular range. So this is the representation of a sigmoid function. Now, very negative score would mean that the probability is close to 0, right? And a very positive score, right, on the right hand side would mean that the probability close to 1, because the left hand side, the probability is drawn between 0 and 1, right? And what would the middle part mean? It would mean a sense of uncertainty, right? So if we have to represent this mathematically, we will say sigma of z is equal to 1 by 1 plus e raised to power minus z, right? So this is the formula. You don't have to really remember this, because what actually matters is what it does. So this sigmoid function turns a score that it gets into what I would say is a belief, right? It turns that into that, right? So the model outputs a probability, right? Probability. It generates a probability. But what are we supposed to do with that probability? We are supposed to decide. And for taking a decision, we need a threshold, right? So a common threshold value is 0.5 because it lies in the center. So a probability greater than or equivalent to 0.5 would mean, like going back to the disease problem, the disease is present, and a value less than 0.5 probability would mean that the disease is absent, that the person is fine, right? So the model says, I am more than 50% sure, so I'm going to say yes, right? So that is what the model tries to convey. Now what happens to this threshold is that it changes based on the context, right? For example, to be more sure, a hospital may consider 0.3 as a threshold, right? 30%, to avoid missing a particular disease, right? So now coming back to the idea of the model does this. It predicts probability using a sigmoid function, and it takes decisions for binary problems, right? And this function or this model is your logistic regression, right? Now, like I previously mentioned also, that despite the name, this logistic regression is not used for regression. It's basically used for classification. It's not used for generating continuous values, because we saw at the end we get probabilities. So basically what does it do? It learns how the input features are affecting the probability of one particular outcome, right? And so by now we know that we have input data, right, which is the medical values, test values, right, of a patient, right? Then there is a combination, which is a linear combination, right? And that gives us score, right? And then we apply the sigmoid function, which provides us with the probability, and the threshold at the end that we apply is going to give us a decision, right? So logistic regression is a decision making model, but under uncertainty, right? So it doesn't just say yes or no, right? It tells us how confident the model is, right? And that gives it more impact in real life. So that's all for logic regression. Let's just